Ever feel like you're just, I don't know, drowning in information? Like there's so much data flying around and you just wish you could get straight to what really matter.
Oh, absolutely. We all feel that. And, often the thing stopping us isn't the lack of data itself, it's how it's put together, or maybe how it's not put together very well.
Exactly. Which is why today we're doing a deep dive into something that's, well, foundational. It's critical, but you don't always see it. We're talking about data modeling.
Right. Think of it like the hidden architecture, the blueprint that actually makes all that data usable and understandable, makes it powerful, really.
So our mission today is basically to unpack the key guidelines, the best practices, especially the evolving ones for building data models that, work well. They need to be maintainable, useful, and fast.
Yeah, perform it.
Yeah.
And we'll definitely get into some key design choices and, of course, tackle that classic debate, star versus snowflake schemas. We have to talk about that.
Consider this your shortcut then, your way to get genuinely up to speed on how data gets structured behind the curtain. So whether you're like prepping for a meeting or just trying to understand a new field, or maybe you're just really curious.
We think you'll have some aha moments. Some things will click.
Yeah, definitely. Let's unpack this. Okay, so first things first. The whole data landscape, it feels like it's shifted massively, right?
Hmm.
What exactly is data modeling now in this kind of new world, and why is it suddenly like even more important?
Well, at its heart, data modeling is still about designing those data tables, right? For users, for BI tools, for applications. It's the blueprint. It shows how data is structured, stored, accessed. The goal is always consistency, clarity.
Okay.
But what's really changed and why it's exploded in importance is because the tech underneath has changed so much. Modern data warehouses, ELT pipelines,
Yeah.
it means data analysts, not just hardcore data engineers, can build these models now.
Ah, so it's more accessible.
Way more accessible. And it means some of the old rules, let's call them sacred cows
Yeah.
of data modeling from, decades ago, they're not always the best way anymore. Sometimes they can actually hurt performance or understanding.
Whoa, okay. That's a big statement. So the whole approach has changed, not just the tools. How did the analytics stack evolve to make this possible?
Yeah, the stacks evolved incredibly fast. Even just in the last, say, 5 years, getting sophisticated data access used to be like only for the big tech companies now. Even small startups can do it.
Right.
The standard way now, for most situations, is this ELT pipeline. Extract, load, transform.
So you pull data from sources, maybe Facebook ads, MailChimp, Shopify, internal databases, whatever, and you load it straight into a warehouse like Snowflake or BigQuery or Redshift.
Exactly. You just dump it in, more or less.
Hmm.
The E&L, extract and load, they become commodities, really. You buy a connector, turn it on, it works.
Okay.
So the real value, the place where you put your unique business logic, is in the transform step.
Yeah.
That happens inside the data warehouse itself.
Ah, after it's loaded.
Right. Typically using SQL may be orchestrated with a tool like dbt. You're writing create table as select statements. It flips the old model on its head. You bring the compute to the data, not the data to the compute.
Huh. So that sounds like a data modeler needs to wear a few different hats then. It's not purely technical.
Oh, absolutely not. You're kind of a product owner thinking about who's going to use this model and how, and you're also the software engineer figuring out how to build it efficiently. It's definitely a balancing act.
So when you're designing, what are the main things you're juggling? Is it just about making queries run super fast?
Speed's important, for sure, but it's only one piece. You're constantly thinking about two main things, your users and the technology.
Okay, users first.
Yeah, users. That means data analysts, data scientists maybe, who are writing their own queries, but also regular business users who just want dashboards and reports from their BI tools. They need different things.
And the technology side.
That's where you think about, okay, query times, yes, but also cost. The cost
Yeah.
models are really different,
Yeah.
Redshift is mostly fixed cost, while BigQuery and Snowflake charge based on compute, which can jump around.
Right.
Plus, you've got transformation speed. How long does it take to build these models? And data latency, how fresh does the data need to be?
So the dream goals are easy for people to understand, works well with BI tools, doesn't take ages to build or run, and doesn't break the bank.
That's the ideal, yeah. But here's the kicker, and this is where it gets interesting. Those goals often fight each other. They conflict.
How so? Give me an example.
Okay, imagine you're building for a sales dashboard. They want it super fast, right?
Right.
Real-time updates. But maybe you're using BigQuery, where faster queries mean more compute, which means higher cost.
Ah, okay.
So you might have to make a trade-off. Maybe the data can be an hour old to save money, or maybe this specific dashboard needs to be fast, But another less critical report can be slower. It's not just technical, it's strategic.
So you're constantly making these judgment calls based on the specific situation.
Exactly. What does the business need? Who are the users? What tech are we using? You make the best call you can, and then you watch it and you adjust. It's never really done.
That makes a lot of sense. And understanding those trade-offs, that's probably why some of those old rules, like from Ruff Kimball's work back in the day, need rethinking now.
Precisely. Kimball's dimensional modeling, his whole life cycle methodology from the 90s, it's absolutely foundational. You have to know the terms facts, dimensions, slowly changing dimensions. That's baseline vocabulary.
Okay, baseline knowledge, but
And this is where people sometimes get stuck just blindly following all of Kimball's rules today, rules designed for a completely different technological era. It can actually lead to models that are harder to understand and slower to query.
slower. I thought Kimball was all about performance. How can following those rules make things less performant now?
Well, remember, Kimball was designing before modern columnar warehouses like Snowflake or BigQuery really existed. He was optimizing for systems where disk I/O was the bottleneck and storage was expensive.
Right. Different constraints.
Totally different. So today, with these new warehouses, a classic Kimball-style star schema with its separate fact and dimension tables needing joins, sometimes that's actually slower than just creating one big, wide, pre-joined table.
Even though that wide table has redundant data.
Even though,
Yeah.
because these columnar databases are incredibly good at scanning wide tables very quickly. They read just the columns they need. Often, the computational cost of performing those joins on the fly is higher than the cost of storing a bit of extra data.
Wow. Okay. So it flips the old normalize everything idea on its head, at least for analytics.
For analytics use cases, yes,
Hmm.
it's a major shift. Remember one project, we built this beautiful textbook star schema, took ages. Then we hook up the BI tool, and the queries it generated were so complex, involving so many joins, the reports just timed out. Yeah, it was a painful lesson. Sometimes the right way, according to the old books, is the wrong way for the modern stack. You have to be pragmatic.
Okay. Powerful lesson learned. So keeping that modern pragmatic mindset, what are the fundamental pillars we need to think about when designing any data model today?
I'd say there are four main pillars or considerations: grain, naming, materialization, and permissioning and governance.
Got it. Let's start with grain. Sounds basic, but what exactly is it and why is it number one?
Grain is probably the single most important concept. It just defines what one single row in your table or view actually represents. Is it one customer, one order, one click?
Give me an example.
Sure. You might have an orders table. The grain is one order. Each row is a unique order. Simple enough. But then you might have an order states table. Here, the grain might be one order in a specific state. So the same order could appear multiple times, once for placed, once for paid, once for shipped, etc.
Ah, okay. So understanding that difference is key.
It's fundamental. So the best practices are: first, figure out the grain. Second, name the table or view so the grain is obvious, like orders versus order states. Third, make sure every single column in that table actually belongs at that grain.
Right, like you wouldn't put the customer's date of birth in the orders table. That belongs in a customer's table.
Exactly. And why this matters so much for you, the listener, is that the grain is clear and consistent. It helps everyone figure out how to join tables together correctly and avoid making really bad mistakes in their analysis. It's step one.
Okay, pillar two, naming. Ugh, naming things. Always harder than it looks. What's the secret sauce here?
Huh. Yeah, naming is tough. Rule number one, though, is just pick a scheme and be consistent. Whatever you choose, stick to it everywhere.
Consistency is key. What about specifics? Table names.
For table names or relations in general, use schemas to group related things. Maybe group by data source,
Got
Shopify
it.
orders, or business area, marketing campaigns, or how processed it is, staging users, analytics users. Always use snake case.
Like this with underscores. Got it.
Yep. And the name itself should be the pluralized grain. Orders, users, page views, product variants. Makes it clear what's in there.
And column names? Any quick rules?
Yeah, a few key ones. IDs always end in id, like ordered, user id. The primary key for the table is usually table name singular id, so ordered in the orders table.
Okay.
Timestamps end in at, like created, updated at. Dates end in date, like birth date, order date. Booleans, the true-false ones, should start with is or has,
Yeah.
is active, has shipped.
Makes sense. It's all about making it readable for humans, right?
Totally. Because humans are the ones writing the queries, interpreting the results. Using a standard SQL style guide helps massively with this too. Just pick one and enforce it.
All right, pillar three, materialization. So we know what a row represents, grain. We know how to name things clearly. Now, how do we actually prepare that data so people can query it fast?
Right. Materialization is basically asking, should this data set be a physical table, pre-calculated and stored, or should it be a view, calculated only when someone queries it?
Kind of like caching and programming.
It's exactly like caching. If you materialize it as a table, you do the work up front, joins, calculations, whatever. Queries against it later will be fast because the results are already there.
But the data might be a bit older.
Potentially, yeah. Depends how often you refresh the table. If you use a view, the data is always fresh because it's calculated on the fly when you query it. But the query itself will be slower because it has to do all that work right then.
And this ties back to the cost models we talked about, Redshift versus BigQuery Snowflake.
Absolutely. On a fixed cost system like Redshift, you might lean towards materializing more because the cost is predictable. On dynamic compute systems like BigQuery or Snowflake, creating lots of materialized tables that need frequent updates can get expensive because each update costs compute time. So you might use views more strategically.
So what's the general advice here, especially for models that end users are hitting directly?
The general advice, especially now with fast warehouses, is usually materialize as much as possible.
Really? Even with the potential cost on dynamic systems?
Often, yes. Because it usually means denormalizing as much as possible, too. Remember that really wide table idea. Instead of a star schema needing joins, you create tables that already have most of the commonly needed information joined together.
And the benefits of that.
Two big ones. First, queries are faster. As we said, no complex joins happening when the user runs their query. Second, and maybe even more important for many users, the queries become simpler to write.
Because they're just selecting from one table, mostly.
Exactly. Those people who aren't SQL experts can handle select from one table pretty well. Add joins, especially multiple joins, or complex CTEs, common table expressions, and the error rate just skyrockets. So wide, materialized tables make analytics more accessible.
Any tips for figuring out what to materialize?
Yeah, look at your query logs. See what queries are running slow. If you see the same complex join or CTE calculation happening over and over again in different user queries, that's a prime candidate to materialize into its own table. Yeah. Pay back the compute cost once during transformation, save it many times during querying.
Smart. Okay, final pillar, permissioning and governance. This sounds like security and rules.
It is, and it's super important. As a data modeler, you have to know what the business rules are around data access and security. It varies wildly by industry, by region, even by specific customer contracts.
Examples.
While healthcare data has IPay rules in the US. If you handle European customer data, you've got GDPR. If you're a SaaS company, your contracts might restrict how you can aggregate or use customer data. You need to know this stuff.
So how does it affect the model design?
A common best practice is to keep sensitive stuff, especially PII. Personally identifying information like names, emails, addresses in separate tables or schemas with tightly controlled access. Don't just sprinkle it everywhere.
Makes sense. You isolate the sensitive data.
Right, and you absolutely need to work closely with your security team or compliance folks. Build the model hand in hand with their policies. Don't build something awesome and then find out it violates a rule. That's not good.
Understood. Okay, so those are the pillars. Now let's get into the big architectural choice, the one everyone talks about, the schema showdown. Star versus Snowflake. Lay it out for us.
Right. So Star and Snowflake, they're the two main ways people organize data in warehouses. Different structures, different strengths, different use cases, often positioned as rivals, but I see them more as different tools for different jobs, sometimes even used together.
Okay, let's break down the Star schema first. You mentioned it earlier.
Yep. Star is generally the simpler one. You have a central fact table. This holds your core measurements, your numbers, things like sales amount, quantity ordered, clicks, whatever you're measuring.
The facts.
Exactly.
Yeah.
And connected directly to that fact table, like points on a star, are your dimension tables. These hold the context, the descriptive attributes, who bought it, what product was it, when did it happen, so customer info, product details, dates.
And it looks like a star, visually, one central table, dimensions radiating out, only one join needed to get from a dimension to the fact.
Correct. And a key thing, as we discussed under materialization, is that those dimension tables in a pure star schema are often denormalized, meaning you might repeat some information, like a category name, within the product dimension table itself, rather than having a separate category table you need to join to.
Why do that?
For read performance, fewer joins means faster queries, generally. So the pros of star are simplicity, easy to understand and build. Speed, faster access, typically.
Great.
Good for BI tools, they often work best with stars. great for straightforward analysis and smaller to medium data sets.
And the downsides.
Well, that denormalization means data redundancy. You're storing the same category name potentially many times, so more storage space needed. It can be harder to manage consistency if something changes. You have to update it in many places. And it's not great for really complex dimensions that have their own sub-attributes or hierarchies.
Okay, that's star. Now, Snowflake schema, how does that differ?
Snowflake starts like a star with a central fact table.
Mm.
But the difference is in the dimensions. Instead of being denormalized, the dimension tables are normalized, meaning you break them down further into related subdimension tables to reduce redundancy. So if you had a product dimension, instead of putting the supplier name directly in the product table, you might have a separate suppliers table and link the product table to it using a supplier id.
Ah, so the dimensions start branching out like the arms of a snowflake.
Exactly. You might have dimensions linked to subdimensions, linked to sub-subdimensions. It creates this hierarchical structure.
What are the advantages of doing that? Sounds more complicated.
It is more complicated to set up, but the advantages are less data redundancy because you store things like supplier names only once. That means less storage space overall. It generally leads to higher data integrity because if a supplier changes their name, you only update it in one place.
Okay.
It's also much better at handling complex hierarchies within dimensions. And because it's normalized, it can be easier to manage frequent updates to dimensional attributes. For really large, complex data sets, it can be more scalable and efficient for certain types of detailed drill-down analysis.
But the trade-offs, that complexity must have downsides.
Absolutely. It's harder to design, harder for users to understand sometimes. Queries become slower because you need more joins, sometimes many joins to bring all the context together with the facts. And managing all those relationships, the foreign keys, makes maintenance more complex too.
Okay, let's boil it down. Quick compare. Star versus Snowflake.
Right. Normalization. Star is denormalized. Snowflake is normalized. Query speed. Star is generally faster, fewer joins. Snowflake is slower, more joins. Space. Star uses more. Snowflake uses less. Complexity. Star is simpler. Snowflake is complex. Redundancy. Star is higher. Snowflake is lower. Maintenance. Star is often easier for simple stuff. Snowflake can be harder. Scalability. For query performance on huge data, Star might hit limits if joins get crazy. Snowflake's structure handles complex dimensional relationships better at scale.
So how do you choose? Sounds like it depends, is the answer.
It absolutely depends. There's no single best. You pick based on your needs. Choose Star if your main goals are simplicity, query speed, you have straightforward dimensions, maybe smaller data, and users need quick, easy reporting.
And Snowflake.
Choose Snowflake if you need to handle really complex dimensional hierarchies, if data integrity and storage efficiency are paramount, if you have very large data sets with intricate relationships, or if dimensional attributes change frequently.
But you also said they can be complementary. How does that work?
Yeah, often in a mature data warehouse, you see multiple layers. You might use a more normalized model, maybe closer to Snowflake, in your intermediate or silver layer, where you're integrating and cleaning data from various sources. Here, normalization helps with integrity.
Okay.
But then for the final presentation or gold layer that your analysts and BI tools actually query, you might build denormalized star schemas from that silver layer.
Yeah.
You pre-join and aggregate data specifically for reporting needs, optimizing for speed and simplicity for the end user.
Ah, so you use each structure where its strengths lie. Normalize for integration, denormalize for presentation.
Exactly. Best of both worlds sometimes.
Got it. Okay, moving beyond just Star versus Snowflake, what are some universal best practices? Things you should always try to do, regardless of the specific schema.
Well, that last point hints at one. Normalize early, denormalize when necessary. Use normalization principles, like separating customers and orders, when you're first bringing data together, cleaning it up, ensuring consistency. It reduces redundancy, makes updates easier.
But then,
For the tables people actually query for reports or dashboards, don't be afraid to denormalize. Create those wider pre-join tables if it makes queries faster and simpler for users. The skill is knowing the right balance for your specific use case.
it's an art as much as a science, huh?
Yeah.
What else?
Future-proof your model. Think ahead. Don't just model for today's exact requirements. If you might expand internationally, maybe include currency code now, even if you only sell domestically today. Think about using UUIDs instead of simple auto-incrementing integers if you might merge data from different systems later. Build it modularly so it's easier to change and add things later without breaking everything.
Good advice. What about ensuring the data is actually, correct?
Right. Ensure data quality and consistency. This means strong governance, Good validation rules. Use database features like chick constraints. Rules like stock quantity must be greater than or equal to 0. Use foreign keys to make sure relationships between tables are valid. Automate data quality checks where you can. Catch errors early.
Makes sense. And finally, how do we make sure all this technical work actually helps the business?
That's maybe the most important one. Focus on business requirements. A technically perfect model that doesn't help people answer their actual business questions is useless. You have to talk to stakeholders. Understand what insights they need, how they want to access data, what performance they expect, then build the model to serve those goals.
So if the sales team needs a real-time dashboard, you build a denormalized table for that, even if it breaks some theoretical normalization rules.
Precisely. The business need drives the technical decision. It really feels like data modeling is becoming less about just knowing SQL and more about understanding the business, communicating trade-offs, almost like being a translator.
Yeah, a translator between business needs and technical possibilities. So pulling it together, what are the signs of a truly great data model?
I'd say 4 things. Accuracy. It correctly reflects the real world, the business rules. It's precise, minimizes errors. Completeness. It has all the necessary pieces of information, covers the required entities and relationships. Flexibility. It can adapt to changing business needs without needing a total overhaul. And scalability. It can handle growing data volumes and complexity gracefully.
And on the flip side, common mistakes to avoid.
Biggest one. Ignoring business context, building something technically elegant but useless, like we said. Second, overcomplicating the model, making it way more complex than it needs to be. Leads to confusion, errors, slow analysis. Keep it as simple as possible while still meeting the needs.
Simplicity is key.
Absolutely. And third, neglecting maintenance. A data model isn't a one-and-done thing. Business rules change, data sources change. You need to update it, document it well. Otherwise, it becomes outdated, untrusted, and ultimately breaks. It's a living thing.
Okay, looking forward then. Where is data modeling headed? What are the big trends?
2 huge trends are shaping the future. First, obviously, cloud-based data modeling. Using platforms like Snowflake, BigQuery, Redshift in the cloud just makes everything more scalable, flexible, often faster. It removes a lot of the old infrastructure headaches.
Right, the cloud enables a lot of this new thinking.
It really does. And the second big one is integration with AI and machine learning. Data models aren't just for humans looking at dashboards anymore. They're increasingly designed to feed data into AM models to help train them, to get insights from them.
How does that change the model itself?
Well, you might structure data specifically to highlight features that are important for an algorithm. You might incorporate outputs from ML models back into your data model. Some forecasts even say that by 2025, like over 75% of data models will have some kind of AI integration. It's making models more dynamic, more adaptive.
Wow. Okay, so let's wrap this up. We've taken quite the deep dive today into data modeling. We've seen it's this crucial, often invisible layer that makes data work.
Yeah, we talked about understanding your users, the tech you're working with, those constant trade-offs. And we definitely unpacked the whole star versus snowflake decision, realizing it's about picking the right tool for the job, or even using both.
And I think the big takeaway connecting it all is that a really well-designed data model isn't just some technical diagram tucked away somewhere. It's actually a strategic asset for the business.
Absolutely. It enables better insights, which leads to better decisions, and now it's even becoming the foundation for powering the AI revolution we're seeing everywhere.
So here's a final thought for you, the listener. As data becomes even more central to everything and AI gets woven into more business processes, how are the data models in your world, in your industry, being built? Are they ready for this future? Are they truly strategic assets?
Yeah, maybe start looking around, see if you can spot examples of good data modeling, or maybe areas for improvement in the data you interact with every day. It really is a fascinating and incredibly important field.
Definitely something to think about. A vital part of the modern data world.